Have you ever pondered about the mysteries that quantum science presents? One of these is quantum entanglement, an inexplicable connection between particles. Dive with me, if you will, into the depths of the quantum realm, where the ordinary laws of physics give way to the extraordinary. Here, we encounter a phenomenon so strange it stumped even the great Albert Einstein. He referred to it as spooky action at a distance. We know it as quantum entanglement. Quantum entanglement was first proposed in the early 20th century, within the mind-bending world of quantum mechanics. It's a phenomenon where two particles become intertwined in such a way that the state of one instantly influences the other, regardless of the distance between them. Imagine two particles light-years apart, yet so deeply connected that a change to one is instantaneously mirrored by the other. A dance choreographed across the cosmos, with no perceivable delay. This phenomenon raises questions that challenge our very understanding of reality. In our everyday world, information can't travel faster than light. This is a cornerstone of Einstein's theory of relativity. But in the quantum world, entanglement seems to break this rule, leading us to question the nature of information exchange. Is there a hidden layer of reality we're yet to uncover? Or does quantum entanglement suggest that the universe is fundamentally non-local, with every particle interconnected in a cosmic web? These are questions that continue to fuel research and debate among scientists and philosophers alike. Quantum entanglement also has practical implications. It's the fundamental principle behind technologies like quantum computing and quantum cryptography, promising a revolution in information processing and security. So, that's quantum entanglement, a phenomenon that forces us to rethink our understanding of communication and the fabric of reality. It's a mind-bending concept that pushes the boundaries of our comprehension, a testament to the enigmatic and intriguing nature of the quantum world. Our journey into the quantum world continues with the measurement problem, another intriguing mystery. This enigma has been the subject of intense debate among physicists, sparking curiosity and driving the exploration of the quantum world. At the heart of the measurement problem is the quantum wave function. This mathematical function predicts the probabilities of different outcomes when a quantum system is measured. Yet, when we do measure a quantum system, something peculiar happens. The wave function, which until that point had been describing a multitude of potential states, seems to collapse into a single, definite state. The act of observation, it seems, transforms the quantum realm from a world of possibilities into our familiar concrete reality. This apparent collapse of the wave function is deeply puzzling. Why does the act of measurement have such a profound effect? And what exactly constitutes an observer? Is it a conscious being, a measuring device, or perhaps the universe itself? These questions have led physicists down a rabbit hole of philosophical contemplation. Some physicists argue that an observer could be anything that interacts with the quantum system, leading to the concept of decoherence. Others propose that the wave function doesn't actually collapse. Instead, every possible outcome occurs in its own separate universe, a notion known as the many worlds interpretation. The measurement problem is more than just an academic curiosity. It challenges our understanding of observation and its role in shaping reality. It forces us to rethink the nature of the universe and our place within it. It blurs the line between subject and object, observer and observed, suggesting that we are not mere bystanders in the cosmic drama, but active participants. Indeed, the measurement problem challenges our understanding of observation and its role in shaping reality. It's a testament to the enigmatic nature of the quantum world, a world that dances on the edge of our comprehension, forever challenging us to broaden our horizons and deepen our understanding. Now imagine existing in multiple states at once. This isn't a science fiction plot, but rather a quantum reality known as superposition. Welcome to the curious world of quantum mechanics, where particles can be in multiple places at the same time, until someone or something takes a peek. Let's start with a simple explanation. Superposition is the ability of a quantum system to be in multiple states at the same time. Think of it as a coin that's spinning in the air. It's not just heads or tails, but both at the same time. However, when it lands or when we observe it, it must make a choice, heads or tails. Similarly, in the quantum world, particles can exist in multiple states simultaneously. They can be here, there, or in several places at once. It's only when we observe these particles that they snap out of this superposition and assume a definite state. This transition from the quantum to the classical world is often called the collapse of the wave function. But how does this transition occur? This is a question that has puzzled scientists for decades. One popular explanation is the Copenhagen interpretation, which suggests that it's the act of observation that causes the wave function to collapse. However, this interpretation is not without its controversies. Another interpretation is the many worlds theory. It proposes that for every possible outcome of a quantum event, the world splits into a copy for each possible outcome. So, in one world, the coin lands heads, and in another, it lands tails. This implies an infinite number of parallel universes. Superposition and the questions it raises about observation and reality are central to the paradoxes of quantum mechanics. They challenge our classical understanding of the world and push us to think in new, often counterintuitive ways. Superposition, it seems, blurs the line between the quantum and the classical, prompting us to question the nature of reality. The mysteries of quantum mechanics continue to captivate us, inviting us to delve deeper into the enigmatic realm of the very small. As we delve deeper into the quantum world, we realize it is a realm filled with enigmatic phenomena and complex mysteries. The puzzles of quantum entanglement, the measurement problem, and the concept of superposition are not just isolated curiosities. They are interconnected threads in the intricate tapestry of quantum science, shaping our understanding of the universe at its most fundamental level. These mysteries don't just challenge our current knowledge, they push the boundaries of what we believe is possible. Quantum entanglement, for instance, defies the classical understanding of information exchange. It's a phenomenon that dances on the edge of the impossible, suggesting that the state of one particle can instantaneously influence another, regardless of the distance between them. The measurement problem, on the other hand, grapples with the collapse of the quantum wave function upon observation. It's a feature of the quantum world that challenges our perception of reality, blurring the line between the observer and the observed. Then there's the concept of superposition, which proposes the simultaneous existence of multiple states until observed. This idea, when extended to macroscopic objects, confronts us with the question: how do these objects transition from quantum superpositions to a singular classical reality? The scientific community is striving to unravel these mysteries. Laboratories around the world are conducting cutting-edge experiments, physicists are developing new theories, and quantum computers are being used to simulate quantum systems. These ongoing efforts are not just about understanding the quantum world, but also about harnessing its potential to revolutionize technology and information processing. At the same time, these quantum conundrums are fueling fascinating philosophical debates, probing the nature of reality and the limits of human knowledge. They invite us to question, to wonder, and to reimagine the fabric of the cosmos. While the quantum world may be complex and enigmatic, it is these very complexities that make it a fascinating subject of study. So, what have we learned from our journey into the quantum world today? We began with quantum entanglement, a fascinating phenomenon that challenges our classical understanding of how information is exchanged. In this peculiar realm, particles become so intricately correlated that the state of one instantly impacts the other, regardless of the distance separating them. It's like they're whispering secrets to each other across the cosmos, defying our conventional wisdom about what is possible. We then plunged into the perplexing measurement problem. This conundrum deals with the apparent collapse of the quantum wave function upon measurement. It's as though these particles behave one way when they're being watched and another way when they're not. The nature of this collapse and what exactly constitutes an observer are subjects of intense debate among physicists, adding a philosophical layer to the science of quantum mechanics. Next, we explored the concept of superposition, which raises profound questions about the simultaneous existence of multiple states until observed. It's as if a quantum object can be in multiple places at once, only deciding where to be when someone or something takes a look. This introduces a challenge in understanding how macroscopic objects transition from quantum superpositions to our familiar classical reality. Through these mysteries, we've glimpsed the enigmatic and complex nature of the quantum world. They push us to question our understanding of reality, nudging us to explore the fundamental principles that govern the behavior of particles at the smallest scales. As we conclude, let's remember that these concepts are not just abstract theories, but are fundamental to technologies we use every day, from computers to medical imaging. Yet, they remain deeply mysterious, reminding us that there is so much more to learn about our universe. As we continue to explore the mysteries of the quantum world, we are reminded of the words of physicist Richard Feynman. If you think you understand quantum mechanics, you don't understand quantum mechanics.